science and technology, developments and their applications and effects in everyday life. Einstein's theory of relativity. Context: Einstein's theory of relativity proven to work even in three-star systems. A study conducted by scientists proved that the legendary scientist was correct about gravity even in the most extreme scales. The experiment. The researchers observed gravitational behavior in a three-star system known as PSRJ 0337 plus 1715. The massive system located 4,200 light-years away consists of two white dwarfs and a neutron star, an ideal example of an extreme scale. After years of study, the researchers reported finding no detectable difference, indicating no alternative theories of gravity were in motion. The results were consistent with Einstein's theory of relativity. The theory of general relativity. In 1915, Albert Einstein presented his theory of general relativity, which proposed that gravity itself was a result of the warping of space-time by massive objects like stars and planets. Einstein's theory of relativity indicates that all objects fall the same way regardless of mass or composition. Things predicted by general relativity include: as light gets closer to the sun, it bends towards the sun twice as much as classical physics, the system used before general relativity, predicts. The perihelion of the planet Mercury rotates along its orbit more than is expected under Newtonian physics. General relativity accounts for the difference between what is seen and what is expected without it. Redshift from gravity. When light moves away from an object with gravity moving away from the center of the valley, it is stretched into longer wavelengths. This was confirmed by the Pound-Ricci experiment. The Shapiro delay. Light appears to slow down when it passes close to a massive object. This was first seen in the 1960s by space probes headed towards the planet Venus. Gravitational waves. They were first observed on September 14, 2015. Alternatives to Einstein's general theory of relativity. Alternatives to Einstein's general theory of relativity predict that compact objects with extremely strong gravity, like neutron stars, fall a little differently than objects of lesser mass. That difference, these alternate theories predict, would be due to a compact object's so-called gravitational binding energy, the gravitational energy that holds it together. However, to date, Einstein's equations have passed all tests, from careful laboratory studies to observations of planets in our solar system.